Hello, today's video is about generative artificial intelligence with synthetic data flow. So we know we are having issues of getting data, sufficient data for robust and efficient machine learning models due to sometimes privacy concerns and in some areas the high cost of getting the ground truth data. So that's why generative artificial intelligence techniques were created as remediative solutions. So the goal is to generate synthetic data while ensuring that these special attributes, the geometry, the coordinates, are unique. And the synthetic data vault is a Python GenAI library which help us generate synthetic tabular data relying on standard geospatial libraries such as GeoPandas. Here is basically for geospatial data, this video. So synthetic data means that the data are artificially created rather than relying on actual events, such as precipitation that help us get rainfall. To get precipitation data, we need rainfall. This is an event. To get wind speed data, we need the wind itself. And the interaction from the radiations from the sun and the land cover gives us the heat, cold, evaporation, evapotranspiration, transpiration, all the data you need. This is the real events that bring us the data, but the synthetic data are created artificially based on the data we get from the actual events. So we don't have enough, we want to increase the number of observations. So you have to have little of the real data, then from the real data you augment, that data augmentation. So that helps maintain the properties of the original data to ensure that the machine learning performs as expected. So in this video, we will be using the conditional tabular generative adversarial networks, the CTGAN algorithm, to augment our spatial data from 200 observations for rows to 400 observations. So the 200s are real from ground truth, they are the ground truth data, and then we add 200 more to the 200 to have 500. So the 200 we are going to add are artificial. Okay. So we need a geodata frame, so along with the non-spatial attributes. So let's go to Jupyter Notebook and start working. So for this purpose, you need to install libraries, pandas, GeoPandas. You install SDV itself, and for plotting or graphic purposes, you need a matplotlib if needed. And we will be using the fig.show. So if needed, you need to install the NB format. Then you import the libraries, import pandas as PD, NumPy as NP, GeoPandas as GPD, and you import geometry as well to have our coordinates for special attributes. And then you import the CTGAN synthesizer. This is the algorithm, the main algorithm. And from SDV metadata, you import the single table metadata. And then from the SDV.metadata. Again, you import the metadata and import the graphic libraries here. In case you receive warning messages, you import warnings. The warnings.filter warnings, ignore. So the data is from this directory. We call it Wells SDV. The data that has 200 observations. So let's see the shape of the data. Print data dot shape. So 200 observations in the 3 variables or attributes. So that's the shape of the data. If we want the columns, print data.columns. So you have X coordinate, Y coordinate in the pH, the potential in hydrogen. And then let's have an idea about the first 5 rows. Data.head. So this is what we get. Okay, so now assuming that this data, because we need a geodata frame, so assuming that this is not a data frame, so you go to pandas geodata frame, from simple data to pandas data frame, then from pandas data frame into geodata frame. So the transformation to geodata frame process. Geodata frame. Let's have pandas data frame. SDF equal PD dot data frame. Data. So we have a pandas data frame. Let's find the columns and see. Def.columns. So this set we get, we don't have geometry yet, so you need a column of geometry. So from data frame to geodata frame. Meaning pandas data frame. Geodata frame. For this we need a geometry first. So to set the geometry, setting the geometry from X and Y coordinates we have in the data set. Geometry equal to the points we have X, Y for XY in zip df dot export df dot y coord. In the bracket, so the geometry is already set. So to get the geodata frame, we call it in this case our real data. So real data and then synthetic data. So this is the real data. This is the first step. So GPD, geo plus geo data frame. Here we have our df, the object, the pandas data frame, and then geometry equal to our geometry here. Then we have the coordinate reference system, which is equal to EPSG. So EPSG 4326. And then we close the parenthesis. So this is our real data. Now let's see the shape of the real data. Real data dot shape. Now you have for 200 rows, 4 columns or attributes instead of 3 for the data frame. Here we can have our data frame shape as well to compare. Dot shape, three. From 3 we have 4 now, and the fourth is the coordinate columns you are looking for. So let's print the head. Okay, play data. First 5 rows. So we have geometry here. While here we can print for the panels data frame as well, and you will see df.head. You have only ph as the last attribute or variables. So this is needed. This is needed. You need this to have the geometry. You need to use the coordinates from the data set. This is needed because it's a special data you are going to multiply. to augment. So now we get to the generative AI now. GenAI. The first thing we need to do is to train the model. We put it here. Training a GenAI model. Here we need to create a metadata from the real data. So we have metadata. Sorry. Metadata equal to metadata is capital M, sorry. Metadata dot detect underscore from underscore data frame and then real data. Okay. Detect underscore from underscore data frame. We already have the metadata. Now we are going to create the synthesizer using the CTGAN. Synthesizer in CTGAN. Initializing and training the model. Sorry. Initializing. Training the model. So let's call it model equal for CTGAN's synthesizer metadata synthesizer metadata. Okay. Once it's done, we need to fit the model using the real data. We are fitting the model on the real data. So we have model dot fit real data. So it's running here. Have to wait for a while. Takes time, little bit, so little bit of time. So be patient. it is function of the number of observation we have, 200, and then the synthetic data is going to take a little bit more time because it's going to 400. So I reduced the issue, I double. So if you want to increase, you can triple. You have 200 data, you need to cover your whole area with probably maybe 800, so it's going to be 400, 200 times 4 is 800, or 200 times 3, 600, but for the sake of time, for the video, I just double it. So from 200 to 400, or you may just need to add 100. So instead of 200, you need 300 to have to cover your area. So from 200 to 300 instead of 200 to 400. So it's up to you. That's your area of study, and the data you have. Meanwhile, let's go to the next step. It's running, but yeah, let's go now to generate the synthetic data, or what we call data augmentation. Generating the synthetic data augmentation. Here we call our object synthetic data. So real data, synthetic underscore data equal to model.sample, number of rows we go to 400, equal 400. So we wait for our model to complete before we run this code, and then we need to integrate with a spatial geometry, the geometry we have, to have our spatial data back. Integration with spatial data, spatial geometry. Here we need to set again the geometry for the sample. So setting the geometry, we are going to copy from what we did before, but using this code. Setting the geometry. So let's call it this time sampled geometry instead of geometry. Sample geometry equal to real data. So from the real data, the geometry you have dot sample we have the length of our synthetic data, so n equal to length synthetic data replace equal to replace equal truth, and random state equal 42. Random state equal 42. Close the parenthesis here. Then we connect to our geometry we have set before. Geometry. Then we reset index drop equal to true. Dot reset underscore index drop equal to true. So we verify sample geometry equal real data dot sample n equal to length of synthetic data. Replace equal to true. Random state 42. Close the parenthesis. Geometry. We take the geometry here. Dot reset index here. Reset index drop equal to true. So it's still running. Let's continue typing the code. So now I'm creating the final augmented geodata frame. Creating the final augmented geodata frame. Here we call it synthetic data, so it's our new synthetic data, which is a geodata frame this time. Equal synthetic underscore data, sorry, equal geopanas dot geo data frame now we need our all synthetic data, so the data we synthesized previously. Then have the geometry equal to the sample the geometry we just have above. Then we have the CRS, which is equal to the same EPSG 4326. Good. Let me verify again here. Synthetic data equal to GPD geopanas geodata frame synthetic data, the whole synthetic data. The geometry equal to the sample geometry here. The coordinate reference system equal to EPSG 4326. So we print the first 5 rows of the augmented data or the synthetic data. The synthetic data dot head to have a shape of it, so I have synthetic data dot shape. Let's see the comparison: synthetic data dot shape and real data dot shape. Okay. So to save the augmented data as CSV, to CSV format, to synthetic underscore data, to underscore CSV, comma separated value, and we call it CTGAN data dot comma separated value, and they have to be a code. Okay, and then we need I can verify again. Good. Here we need to verify, we need to evaluate our synthetic data. So we evaluate real data versus synthetic data. Here we need to import the run diagnostic from the SDV evaluation. So the first thing we need to do is to from SDV dot evaluation dot single underscore table import run underscore diagnostic. And then we have the diagnostic now as an object. Equal to run underscore diagnostic parenthesis the real underscore data equal to real data synthetic data equal to synthetic data then metadata equal to metadata. And then we close our parentheses. The next step is to measure the quality of the data, so the statistical similarity between the real data and the synthetic data. Statistical similarity between the data and the synthetic data. Here we need to import evaluate quality from SDV evaluation SDV.evaluation.single underscore table import let's go on with my code. Import evaluate quality underscore evaluate underscore quality. So now quality report as an object, quality report equal to evaluate quality, evaluate underscore quality, parenthesis. Let's close at the same time here. We have real data, metadata, real data, synthetic data, and metadata. So the next thing is we verify here real data, synthetic data, metadata. So that's measure of the statistical similarity between real and synthetic data. Evaluation of real data versus synthetic data. Have run diagnostic, import it, diagnostic or run diagnostic. So real data equal real data, synthetic data, metadata equal metadata. Okay, let's continue. And then we need to, if you need to get details from the report, quality report, you need to get detail. So quality underscore report dot get underscore details from the column shape. Column shapes. Okay, so the next thing we need is the visualization. So 1D visualization, 2D visualization. Visualization of real versus synthetic data. Have a 1D plot of pH. Let's have it. So from SDV dot evaluation dot single underscore table, we need to import get column plot. Get column underscore plot dot underscore column underscore plot. Then we import plotly dot express as px. Then we have our figure object equal to get column plot. So get underscore column plot, get underscore column get plot, get underscore column underscore plot. Sorry. So have real data equal real data. Have synthetic data equals synthetic data. Comma column name pH column underscore name equal quote pH comma then metadata equal to metadata. Then we have fig.show out of the parentheses fig.show. Okay. Then this time is 2D plot. Plot of pH versus longitude. Here we are going to get the column per plot from SDV dot evaluation dot single underscore table. We import get underscore column underscore underscore plot. verify SDV evaluation dot single table import get column per plot. Okay, our object figure for get column per plot. Plot real data equal real data. Synthetic data equals synthetic data. You have two columns here, so column names equal to bracket, we have pH, and the longitude is x coordinates, so x color. With the brackets, and then metadata equal metadata. And then at the end, figure show. Here, if you want to have the pH versus latitude, we just copy this here and modify, copy paste and modify latitude here, and latitude is y coordinates, pH and y coordinates. So the only two changes you need to make. Let's continue adding more rows. So now, if you want to save the model, before we save the synthetic data as CTGAN, now it's the model itself, saving it and loading it for next steps if you want to continue. So saving the model. Model.save. You call it as you want. My model. Dot pkl parenthesis code. To load it, so loading the model from SDV.utils import load synthesizer, load underscore synthesizer. Then model equal to load synthesizer my model dot pkl. My model dot pkl. Okay. Want to continue, yes, I'm not going to do this because for the sake of time. Model.sample, number of rows 400. So we are still waiting for this. So once done, we will run the codes I'm typing. But for now, we wait. And then now there is another way. If you want to customize, this is the direct way. If you want to customize the model, we have a CTGAN customization method. Okay, we call it custom model. Equal CTGAN synthesizer parenthesis metadata epochs equal 50. I take 50 because of the sake of time again. You can add more if you want to, and the verbose equal true. Okay, and continue. This is the custom model we are going to fit now. Metadata epochs 50 verbose true. CTGAN synthesizer. Yep, okay. So fitting our custom model. Customized model. Custom model dot fit custom underscore model dot fit on real data. Sorry. Custom model dot fit real data. And then we verify the improvement of the custom over the data we ran before. So verifying model improvement or model quality data improvement, data quality improvement. That's model improvement by evaluating the custom synthetic data. Customized synthetic data. Here we first need our custom the synthetic data customized as well. So have synthetic data underscore customized. We have real data customized, synthetic data customized, real data, and synthetic data. So customize synthetic data customized equal to custom model, custom underscore model dot sample, number of rows equal to 400. Okay, so we are going to evaluate the quality report. Evaluation. Quality report equal to, okay, it's already done here, right? Good. Run already, that's good. Let me finish typing and then we'll go back to where we stopped. So quality report equal to evaluate report. Should we evaluate quality? Evaluate quality, rather evaluate quality, the real data, synthetic data underscore customize in the metadata. And close the parenthesis. Okay, let's go back to the model and check everything. Okay, we stop here, right? Model.fit. We fit the model. Now the synthetic data. Sorry. Okay. We have the synthetic. We stopped here. Yeah. So let's continue. We need to integrate with the special geometry. So the sample here we wrote the code. So sample geometry called real data.sample. And this the sample geometry. Then we have our new geo data pandas. The new geo data frame. So synthetic data equal to pd.geodata frame. All synthetic data, we set the geometry equal to our sample geometry here, where we took the geometry from the real data. Put here. Remember. So we run it. Now we have the synthetic data dot head. And you have geometry here. So this is a geodata frame now. And you have the shape. You have 4. So the fourth is the geometry. So if you want to compare 4 and 4, so we have geometry, the real data, geometry, and the synthetic data. So now, if you want, we save it. Of course, the purpose is to have, so we save it, we call it CTGAN data.csv, and we run this code. It's already saved. If you want to go and find our sorry, okay, to go to where our saved augmented data is, we go to C users, and wherever our Anaconda is installed, and we call it CTGAN. Voilà, CTGAN data. February 2021, February 21, 2026. That's today. And we click, we open it. My computer is slow. Sorry, my computer is dying. Everything is slow. So this is what you have in our synthetic data. And we have actually our 399. So from 0 to 399 is 400 data. So here 401. So 400 data. So we are good with it. Let's come back here. The difference is here, or you can see it here is 200 for the real data, 400 for the synthetic data. So let me flip it so that we can see it everywhere. Call it real data here, the synthetic data. We see the augmentation. Oh, sorry, mistake. There is typo. I put K here, so that's the issue. Okay. Okay, 200 to 400. See here clearly, and we already save it. So here is to evaluate the real versus synthetic data. By running the diagnostic. So SDV, sorry, again, typo. Okay, the report validation overall score 100%. That's good. Now you want the statistical similarity between the real and the synthetic data. You run. Where is the mistake? Okay, again typo. Single data instead of sync data. Okay. So we have shape score 78, column pair trends score 17, overall score 47.92, 48 almost. That's not, depending on the situation, that's not good, but we need overall score higher than that. So all will depend on the data, the size of the data you have. Yeah, that's how you run it, and if you are satisfied, you continue. If not, you seek for more data. And as you here is the detail from the quality report, the column shape, x coordinate, y coordinate, pH and geometry, the matrix and the scores. Good. Now the visualization. After the matrix, visualize pH only. So the fig.show gives us, after writing this code, and running it. That's wrong. Okay, it takes time. So we see here the real data and the synthetic data. The synthetic data is magenta here, cyan, and the real data darker blue here. And then we see how they are using the CTGAN, the frequency, synthetic data, real data. You see them, how they are. And the pH, 7, 7.5. So the value is from 6 to 9. And the frequency is here. Then we need the 2D plot that pH and the longitudes, the x coordinate. Wait a little bit. So we have the longitude on this side, then we have the pH, and you see how they are distributed. You have the real data, you have only 200, and you have synthetic data. So our synthetic data, you have 400 data. So how they are distributed over the region according to the longitudes. Okay, now you want with the latitudes, so the y coordinate. We just change, right? Y, x coordinate by y, and here latitude. So here it versus our latitudes. So latitudes go from 13 to 16. That's the parallels, and you see the distribution of our pH with regard to the latitude. So we have real data, synthetic data, synthetic data, real data, synthetic data. That's good. So you save the model. The model saved. If you want to load it, import load synthesizer, the model equal to load synthesizer, my model you saved. Then if you want to continue with the analysis, you type this code, but going again to take a little bit of time. So I prefer to go to the customization of the model. So 2 ways. You just have your model equal to the CTGAN synthesizer, and you have your metadata, or you custom it and then you put the epochs, you put the variables. So this is the only difference here. In the model.fit, it's on real data. So what we did is here, we added this to customize it. If you compare to our previous model, it's here, the model, CTGAN synthesizer metadata. So to this we the epochs and the variables. That's all. So we run this. Wait, we already run? No. Okay. Now we fit it on the real data, custom model, customized model. I don't think it's going to take more time again, but yeah, a little bit. But this is necessary for the comparison. We are at the end. I'm sorry if you are hearing some noise from just beside me. There are kids there, anniversary, so I'm sorry. So out of 50 we are at 6%. I should have put just 10 here. I'm sorry, it's already done, so you have to wait. Epochs out 4 out of 50. You have to wait until the 50s are done. 5 out of 50. Okay. It's running, so be patient. I should have done it otherwise. Just reprocess the image, the video. That's also an option. Okay, almost done. 48 out of 50. Okay, good. So this is the custom model dot fit from the real data. So now we are going to verify. It means that we needed to verify whether our custom model, customized model, perform better than the model we ran before. So we have to have also the synthetic data customized here should be equal. The sign equal is missing here. So we run 400 rows. So it's already run, and now we need the quality report of it. Synthetic typo here. Real data synthetic here also. Typo metadata. Customize. So this is what we get. Does it perform better? Overall score 72, 21, 47. Let's go to the previous report we had. Mm, 72 over there. Here is 78. So on this side is better, but the overall score doesn't change too much. It's 47.21, 47.92. Here the column per trends is 17.33, then the customized is 21. So 21, that must much improvement. Yeah, 47, 21, 17 over there, 72 here, almost 73 over there is 78. So the customized does not really improve the quality. That's not too much improvement. So yeah, and we are already at the end of this video. It's a little bit long, longer than I expected, but yeah, I hope you learned something from it. But the main game here is you have little data, you need more to validate your research. How would you do if you cannot have ground truth data? The little ground truth data you have, just use generative AI to augment the size of your data. Yeah, so SDV helps with GeoPandas, help managing the geospatial data as of now. And then you have also GeoAI, which is a Python library. GeoAI also could help. GeoAI is very specialized in geospatial data. So it's GeoAI, artificial intelligence for geospatial data. But here we manage with it. So thank you very much for watching, and I hope this video will help you. It helps some of you who are doing research on geospatial data or are lacking data. Yeah, they can augment the size of the data, and that would be that they have to look closely to the reports, the quality reports, to evaluate whether they're really correlated or not, the real and the synthetic data. Yeah, you have to look at that. It's important to have higher score here. Overall score 47. That's have 80 something like that's good, but here is good. Here's 100. That's valid. The validity is good. Structure's good. Overall scores good. But the problem with my data here is below. I would expect to have higher scores here if I want to continue using it for my research first, my research, or definitely to have higher score here. Okay, I would prefer to have higher score here. So thank you for watching, and see you next time for another video on GenAI, but this time it's going to be with Gaussian copula. So SDV Gaussian copula here. So thank you very much. See you next time.